Welcome again in Physics Within You for the segment Physics for You. So we will now do the Bragg's law for diffraction. Bragg's law. So Bragg's law is based on the diffraction of a radiation, that is X-ray here. Why X-ray? Have you ever thought? X-ray has a wavelength of order of angstrom, while your lattice, you can say the crystal structures. So the lattice gap or lattice spacing, which means the aperture for the diffraction, is order of angstrom or nanometer. So both are comparable. If we can compare the two, then the diffraction can occur. So X-ray is suitable for study of these materials, and that's why X-ray diffraction. So let us understand how this diffraction occurs. So we can consider, like in optics, we have some planes. So these are the some planes. Here we called it lattice plane. Each plane is separated by interplanar spacing. You know about that. That's your DHKL. And that happens for the infinite number of layers. How many numbers a material can have? As far as the diffraction understanding is concerned, only two layers is sufficient to understand. So first we understand that how the reflection phenomena occurs. So irradiation is allowed to fall on a material surface and it get reflected. So simple reflection, nothing else. So it has some normal. It make an angle of, I mean to say phi with the normal. What we do in the case of optics. But here we will do something different. Now understand this diagram, the radiation is coming, this is the normal, this is making angle phi as I have shown here. But there is another angle here. And in the X-ray diffraction, we call this as the incident ray. Understand? Incident ray. And this is your plane, lattice plane. So angle between that, this theta is called the incident angle. Remember that in optics, we usually define by this, but here we will define by the angle between lattice plane and this ray. So remember, this is the distinction between the optics and here XRD. So that is the one of the thing that you must aware about that. Now, to have a diffraction, I need the number of reflection so that they can combine. So you can see the 1 over the ray is coming here and reflected in this way. So that you know is a 1. But it has to happen simultaneously with the second layer also. And in that case, there will be a path difference. And you know the path difference, what should be? Let's say that delta x. It should be of order of wavelength n. And is can be 1, 2, 3, and so on. So what is the wavelength of this incident ray? Will give you the path difference. So for the constructive path difference, this should be interior multiple times of the wavelength that you know from the diffraction study. So I assume now the case of the as it's a wave phenomena. So we take consider for the example of wavefront. Let's say this is the wavefront which is coming instead of ray. Now this wavefront will reflected also or outgoing way. It will move like this. So everything will be the same apart from the fact that here is a path difference generated, and this path difference which is generated here is shown by the here shade. This path difference is shown here. So I am showing this in the very more elegant way so that you can understand that there is a the same thing is here. Now you know this angle is theta, this blue angle is phi, because theta plus phi are 90 degree, that means their complementary angle, and this is the, you can say, the triangle, because this is falling wavefront is always normal to the ray. So this is your 90 degree. So as you know that this angle is theta, so this angle has to be theta here. So sorry, phi. If this angle is phi, this angle, the angle parallel to it also should be phi. So what is denoted here? This angle is your phi. So you understand that? If this is phi, the another angle has to be theta by this. So this angle is your, or this angle is your theta. So likewise here. So this is theta. I hope you understand what is phi. This is phi, and that's your theta, because this angle is a perpendicular way. So you can understand this is the part. So let's say this AB your, and this lattice spacing. This is the this part A and B. So lattice spacing is there. So this is your D HKL. So what with the part difference? Part difference will be this much. This is the part difference right now. So that's your CB plus BD. And you know this angle is theta. So what should be value of this one? Sin theta DHKL, or DHKL is sin theta, whatever you say. So this is the value you got. So what should the part difference? Twice of this value, because these are the same. So the part difference will be CD plus BD equal to 2D sine theta. So we have the path difference of n lambda, and for the constructive diffraction, and the part difference what we achieve here is 2D HKL sine theta. So this should be equal to get the constructive diffraction, and that's your Bragg's law. For the diffraction pattern to occur, we have to satisfy these two to be equated, and we get this relation. So this is your Bragg's law. So let us summarize this one, that how does the X-ray diffraction occurs? So it occurs via a incident X-ray strikes on the parallel planes of atom in a crystal at an angle of theta, where theta is the angle with the incident ray and the lattice planes, not with the vertical. So a part difference is generated that is equivalent of 2D sine theta, and they have to satisfy some constructive interference for the diffraction pattern, and that's why you get X-ray diffraction to occur with the formula what we have learned. Now, what machine do this? So there is so many machines about that, Rikaku itself. Here I have shown the broker one, the model D8. So you can see this part there is a chamber which is almost evacuated or something. You can say this is the electron, maybe to say electron gun is there, which bombard on the some target material. Let's say copper. In the most of the cases, there is a filter section. Usually, a nickel filter is used, and there is a sample holder. If you can see here, there is a sample holder where sample is placed. So the light, the X-ray, I mean to say, fall on this one, and it is detected by there, and this chamber moves. This angle moves. So this is theta to theta scan basically. So I'm not going to detail about that, just to remember the Bragg's law right now. So Bragg's law, you know the formula about that. So we are just summarized. Now I'm giving the formula that n lambda equal to 2d sine theta, where you know the what is n and the order of diffraction, and the order of diffraction is usually equal to 1. So your formula is very simple. It's now the lambda equal to 2d sine theta. So theta and d, so there is nothing much special. The only thing that I have to show, that what I was saying, that in case of the regular crystal, or I mean to say the long order crystalline features, like you have I mean to say X-ray diffraction pattern like this, you can observe. This is the polycrystalline sample, but however it has the long range ordering, so you can see the electron diffraction pattern. Yes, it's the electron diffraction pattern, where you see this kind of diffractions shining in the space. So you can compare with these two, they are comparable. While in the case of, I mean to say, amorphous material like say glass or the semi-glass or the crystalline, or say, I mean to say, amorphous property mixing is there. So we can identify, here we can see some peak is there. So yes, some crystalline feature is there, some kind of order is there, but here you see there is nothing, there is some a broad hump is there. So this shows that there is a amorphous nature. So this material is a combo of amorphous plus crystalline feature. So what is that? That is the application of XRD, X-ray diffraction, that we can understand when we allow the XRD to fall on our material. We understand our material is crystalline or amorphous or mix of that. In case of this, I mean to say non-crystalline features or polycrystalline features, we get rings. Here you can say the electron diffraction comes in the rings formation. Here the electron diffraction gives the use the spots. I will show you the d-spacing also from the TAM images. So let us see. So this is your XRD pattern. You know, for the crystalline feature, you get the peaks. So we are here peaks there. So not a, you understand? It's a crystalline. It's not amorphous. Why? Because we have some sharp peaks, right? So we have the diffraction pattern, electron diffraction pattern. In the visualization way, you can see this one, the pattern. We have indexed with the Miller. We have indexed the Miller planes there, and Miller indexing is there. This is the HR PAM image. So what we have there, you can see the formation there, and you can understand the gap between the layers. So this is the what I have shown there. If you want to compare it with the picture with X-ray diffraction, I have shown. I have shown this lattice. So that diagram you can say compare this easily compare. So we can know the where the d-spacing is there. So this is the d-spacing between two yellow lines there. So you can estimate how the X-ray will coming and going, and you can detect the X-ray diffraction or the electron diffraction. Basically, this part is done by the electron diffraction. So by combining these two, we get the structure of a material. So that's very useful. Both phenomena use the diffraction, one for X-ray, another for the electron, right? So I hope you get to this point, how the X-ray and XRD used. So this is the application of the Bragg's law. It determines the interpolation spacing. You have seen that D you can understand. Otherwise also crystal structure determination. I have said that whether a material is the polycrystalline or crystalline or something else, you can understand via studying the XRD pattern, diffraction pattern. And if the material is cubic, you can understand how the what is the lattice constant because you are knowing the D. So once you are knowing the D, you can get the value of that one also. So that was the application of the Bragg's law. So Bragg's law very important for the material scientist. So for the researcher, this is very important. That's remember. So let's do some of the numerical so that we can understand. I have taken the easiest numerical because numericals are always easy if you know the concept. And this thing I always said. So here a beam is given you that what is the beam length is wavelength is of 1.54 angstrom and angle is theta, right? So interplane spacing. That's a simple. If I say the material is cubic and say that what is the lattice constant, that you can do also. So I don't think this is very difficult because lambda is given to you, theta is given to you, and you will use one. Formula is 2d sine theta and lambda. So just to replace the values, 2 is 2, no problem. D is to estimated sine theta, sine 30 means half, right? N is 1, lambda is given, so no problem. Do it fastly. Order we know this is in angstrom, so we will do just right now. So your D equal to the same of order of lambda, that is 1.54 angstrom. So you see there is no difficulty. If I say A, you can estimate A if it is cubic one here. So that you can do right now. So it is very easiest thing to happen if you simple numerical is there. And I hope you can do all this thing when. But one of the thing, if I ask you, can you tell me that why this is value is 1.54 always? I have given the answer. In fact, when I was explaining the X-ray part, how the X-ray occurs, I have given the answer. This is related to why I should say. So my question is very obvious. Why only lambda equal to 1.54 angstrom appears for XRD? Whenever you see the problems, you will see this is the value of lambda equal to 1.4. It's because you want to know. Chaliye, you do some comment for me. Then I will answer. Now the answer is something related to that part in which I was talking about how the X-ray become the electron falls on a target material, and that material is copper, then the wavelength is 1.5. If that material is not copper, it will be something different. So answer I have given perhaps, but if you want to know more about that, how it happens, so I can tell you about that thing. So comment about that. If you found that this topic is interesting, the friends and others, then please share it, like it, subscribe it. वैसे मैं कहता नहीं हूँ कोई, but I'm saying this because this is something special if you want to understand. So we are closing this video part for the Bragg's law right now with this. So बने रहिए हमारे साथ. Thanks for learning with us. Bye bye till then.